This is live, but live where? Huh? Swinky. How do I share the link? Okay. Okay, this one. Okay. Try this one now. Can someone try this? Yeah, that's the problem of being that's the problem of doing information theory. So when someone asks you what do, you say IT, and they're like, oh, you must be very good at IT, and I truly suck at IT. So okay, it is working. It's working good. Okay. So we're finally done with week 3, and now let's move to week 4, which is primarily the general channel coding theorem, which I mean it looks long and complicated, but really it's I mean, today we're only going to focus on the general channel coding theorem, and really, it's most of the ideas we already covered in the binary symmetric case. Let me put this on top, and okay, all right. So in the general channel coding theorem, so let's remind ourselves what the setting is. So the setting is again. Let me use the color. Different color. What is that different color? Okay. So in the general channel coding theorem, I have Alice, the encoder, has NR bits, has a message with NR bits, wants to encode it using some encoder to a code word in script X to the n, so over some general alphabet, not necessarily binary. Transmit it over a channel. So this channel has some channel law. So it is basically, a probability transition matrix, a conditional probability distribution that says if you transmit a vector xn, what is the probability of observing a vector yn? The y does not have to be over the same alphabet as x. So y, this is over some general alphabet script y to the n, and then wants to decode to some m hat. So it's very abstract, right? Some alphabet script X here, some alphabet script Y here, a probability transition matrix going from script X to the end to script Y to the end. Okay? So at least in this generality, it could even be, say, a deletion channel or something like that, right? Something complicated that we don't know how to solve. And what do we want? We want a maximum probability of error. So we want for every message the probability over the channel noise that m hat not equal to m, that the probability that the decoder is unable to decode correctly should be smaller. Now, if this is all that we wanted, then of course life would be easy, right? What could you do? You could just set r to be equal to 0, right? Transmit nothing at all, and then output, oh, I transmitted nothing at all, and everything is good, right? So really, it's not just that you want a small probability of error. You want a small probability of error, this to go to 0, but also you want r to be as large as possible. Right? So you simultaneously want r to be some positive constant, as large a positive constant as possible, while ensuring that the probability of error goes to 0. Right? Just like a generalization of the binary symmetric case. Okay. So the converse, you've actually already seen this before. It's really just the same thing. let's very quickly review it. So you have NR message bits, which is precisely the entropy of the message because the message is uniformly distributed there. Then by the definition of mutual information conditional entropy, you decompose the entropy this way. Use the data processing inequality to use this inequality. Use Fano's inequality for this one. Use the independence bound to bound the. So this is in a couple of steps. So this mutual information is equal to h of yn minus h of yn given xn, right? H of yn by the independence bound you can bound like this, and the conditional entropy because it's a DMC you can bound like this, right? And then combine them term by term together, and you get summation of these mutual informations. Now, for every one of these terms, the corresponding xi. So over here, how do you interpret the corresponding xi? This is yeah. So the way of interpreting this xi variable over here is you look at the ith coordinate of your codebook, look at the fraction of x1s, look at the fraction of x2s, look at the fraction of x3s, right? So so that gives you a probability distribution over the x alphabet, right? So that corresponds to your input distribution for the ith symbol over here, right? And then your yi corresponds to, well, what is the probability of observing y equaling a certain value over here? So again, you have 2 to the nr code words, each of length n, and now you're focusing on the ith coordinate of each code word, and you're asking yourself, what is the probability of observing a particular y, like of observing y equal to the ith coordinate of y being equal to a particular value. So the channel itself is fixed. The channel is given by some we've been calling it q of y given x, right? So this q of y given x of the y given x is fixed. This p sub x of x we can choose. We can choose a codebook with different fractions of zeros, ones, twos, or whatever over here, right? So if you want to maximize this mutual information, this is basically the same as maximizing the just a single letter expression, because it doesn't matter what the I is. It's going to be the same optimization. This q of y given x is going to be fixed. All you can do is change the fraction of zeros, ones, twos in each coordinate separately, right? And when you do that maximization, then you'll get some C over here. So this maximization is basically like choosing the input distribution to design this codebook over here. Okay. Now, notice that, by the way, and we've already discussed this before. So this is of course much more desirable than choosing than optimizing over all possible p. So maximizing over p of x is much better than maximizing over p of xn's, right? We already noticed that before. Notice this should still feel surprising to you that we can get away with this. We can do this. We can behave so lazily, because really, like when we are maximizing this mutual information over here, this single letter mutual information, we are just pretending that in this ith coordinate, all we have to care about is the number of, let's say, zeros, ones, twos, right? If it's a ternary alphabet, we only have to care about that, nothing else. So we don't have to therefore worry about the structure of the code. We don't have to worry about in the jth coordinate where are the zeros, ones, twos, right? So in principle, you could imagine a terrible code where all these code words are identical, all these code words are identical, like these code words are all 0, these code words are all 1, these code words are all 2. That would be a terrible code book, right? That would be a truly terrible code book. But when we are doing this maximization over here, we are somehow just pretending that all that matters is the fraction of zeros, ones, twos in a particular column, without worrying about how they interact with different columns, right? But the beauty of Shannon's theorem is that actually it suffices to do this optimization. So sure, you could be choosing a code book like this, but if you choose a random code with a fixed fraction of zeros, ones, and twos, but do it randomly, then for column I, the zeros, ones, twos might look like I've drawn over here. But for column J, maybe the zeros, ones, twos will be something like this. For column K, there'll be something different, right? So if I'm choosing things at random, then all that matters is the correct fraction, choosing the right fraction. And since I'm choosing things at random, therefore the resulting code words will actually behave reasonably. Okay? So this is still magic. Even to me, it still feels like magic that we can do this single letter optimization instead of doing this n letter optimization. For the from the converse perspective, we only have to worry about the single letter version. From the achievability perspective, we also only have to worry about the single letter version, but our analysis, looks at n letter vectors. Our analysis looks at, xn vectors, yn vectors, and so on, right? So our analysis does indeed have to worry about those vectors, but somehow in terms of achievability, the rate also depends on the single letter vector. Okay, I'm just being philosophical here. I'm just pointing out the fact that we've already discussed before, but I just wanted to emphasize it again, that the channel coding theorem should still look magical to you. Okay. All right. So then yeah, and then let me point out one other thing, slightly stronger than what we discussed before, which was, okay, so we noted earlier that if we could just have stopped at this point over here and say that the rate can be no larger than the supremum over all p of xn, this n letter mutual information divided by n. And this is an upper bound on the capacity, right? Optimizing over all the possible n letter code books. But so the physical meaning of this, like if you choose 2 to the nr code words, this is like saying I'm going to choose my p of xn to be 1 over 2 to the nr for the locations where I'm choosing my code words. Like if I'm choosing a deterministic code book, then I choose p of xn is 1 over 2 to the nr for the code words and 0 otherwise, right? For all the other sequences, I choose them to be 0. But notice in this setting, I could also choose, a different distribution. For a particular message, I could have multiple different code words for that message, right? That's also allowed in this setting over here. Okay? So this is just so that you get some intuition about what it means to have what this supremum over p of xn means. It just means look at all possible probability distributions over n letter sequences and then compute this n letter mutual information divided by n, and the rate can be no larger than this quantity over here. We already saw this because of these chains of inequalities, and if we just stopped over here, then we would already get that your probability of error cannot be larger than this. Right? We saw this last time. I'm not going to repeat it. But there is something called Feinstein's lemma, which says that not only is this an upper bound, it is actually also achievable. Okay. So even for non-discrete memoryless channels, for example, the deletion channel or intersymbol interference channels and so on, where we cannot compute the single letter capacity. Okay, so it's hard to compute that single letter capacity. We don't know what the capacity is, but we actually know that it equals this supremum object. Okay? So it's not like a very useful result in the sense that it is a priori, it's not at all obvious how to compute this object for the deletion channel, right? But at least we know that there is a supremum. In fact, with some more effort, you can show that this quantity converges for large classes of channels, even if they're non-discrete memoryless. Like there's some term for these channels for which this quantity converges, and in that case, you can compute the. You can claim that the capacity exists. Okay, it's not that that this is a non-converging sequence, and therefore you can't hope for the capacity. Okay, but again, like these are sort of supplementary remarks. These are more advanced topics than we'll be covering in this course, because in this course we'll focus on discrete memoryless channels. But it is useful to know that even for much larger classes of channels, these things exist. All right, so philosophy. Okay, one more remark, and then we'll move on to the main achievability for discrete memoryless channels. So this remark is something again that we already remarked before. So this maximizing P of X over this mutual information is not always achieved when the probability distribution is uniform over the alphabet. So one example is the Z channel, which we already looked at before. So let's say zeros and ones inputs, zeros and ones outputs, and with probability P, ones get erased, zeros never get, ones get flipped, zeros never get flipped. Okay? And when you do the calculation, so you write the corresponding mutual information, and then you maximize over the Q, you maximize the mutual information between X and Y for fixed P. So you fix the P, fixed P, and then you maximize this over Q, and then the corresponding capacity will be something. Okay? And it's basically algebra. There's no easy way of doing it. Easier way of doing it. Okay, so prefatory remarks aside, now let's look at the general achievability. So even though the general achievability looks long, let's see. I'll hope to try to finish it in the 15 minutes or so we have left today. Really much of the analysis is quite similar as before. I've just done it in very large detail. So it should, even though it looks intimidating, it actually is really similar to stuff you've already done before. Okay. Let's see. I won't push it. So you choose the rate corresponding to C minus epsilon n. So C is just this maximum over P of X, the mutual information between X and Y. And then you choose 2 to the NR code words, each of length n, where every symbol is drawn IID according to P of X, Px of X. Okay. So for example, for the Z channel, it won't be zeros and ones with equal probability. Maybe zeros are likelier than ones, maybe ones are likelier than zeros, but according to a specific optimizing Px over there. Okay. All right. So corresponding to the optimizing P of X over there. All right. Now the encoder is basically, if you want to transmit the ith message, look at the ith code word, transmit that. What is your decoder? So we're going to look at a typical set decoding. So what does that mean? Like if you get a particular Y, look at the corresponding conditionally typical set of X's, and if there's a unique code word in there corresponding, like in the corresponding conditionally typical set of Y's, then output that. Otherwise, declare an error. If there's no code word, or if there's more than one code word, then declare an error. Okay. Again, so this typical set decoder is a weaker decoder than the maximum likelihood decoder. We already saw that in the binary symmetric case, right? But again, in this case, it will still be good enough. Okay. One other thing, we'll weaken it even slightly more. We'll say, even if the Y is not typical, then we'll declare an error. Okay? The typical set decoder, in principle, you can look at any Y, even atypical Ys, and then look at conditionally typical X's for those, right? But we'll even demand that the Y we receive be typical. Okay. So, for example, in the binary symmetric case, if your code book is if your X vectors are roughly half zeros and half ones, then you expect the Y's to be half zeros and half ones, right? You expect the Y's to be half zeros, half ones as well. Now, if you happen to receive a Y which is 2/3 ones and 1/3 zeros, you could still look for code words which are within Hamming distance NP, right? You could still define a conditionally typical set decoder, but we're just going to declare an error. We're going to say, oh, something unexpected is happening. I don't know if I can trust my analysis, so I'm just not going to bother. Okay? So I'm also going to demand that Y be typical over here. Okay? And similarly, we'll also demand that the X's we decode to are themselves individually typical. So if I see a Y over here, if I decode to a particular X, which is at a certain Hamming distance, I'll also demand that this X itself have Hamming weight close to, for example, in the binary case, Hamming weight close to n by 2, n by 2. For other channels, have a type close to the optimizing input distribution of the code book. Okay? So basically, I'm going to demand all three types of typicality. X should be typical, Y should be typical, and the X should be conditionally typical with respect to the Y. Right? And why do we do this? Really, just for the sake of analysis. Actually, a priori, you don't have to do this, right? But it just makes analysis easier. All right. So, yeah, wait, what did I want to say over here? All right, well, we already discussed this. Okay, fine. So, okay, so let's begin by doing some analysis a little bit carefully. Okay, so let's see. So what is this lemma saying over here? This lemma is saying, I mean, there's a lot of algebra, but basically what is it saying? It's saying, yeah, okay. So first of all, let's temporarily forget the outer probability. Let's just look at this quantity over here. This is some event, right? So what is this event saying? It's saying that the number of code words in a code such that the code words are not in the typical set with respect to the optimizing input distribution is more than a certain factor of the size of the code book, right? So if you think about it, if I choose code words, if I choose these x vectors at random, then I expect most of the x vectors to be, most of these x vectors, like if I've chosen 2 to the nr code words, 2 to the nr code words each of length n, where each entry is sampled according to this p star of x, right? Then I expect p star x of 1 symbols to be according to like that fraction to be 1s, p star x2 to be 2s over here, and so on, right? I expect the type of this vector to be close to the underlying distribution from which I've sampled. Right? We've seen these concentration inequalities before. We've seen that the expected type is going to be very close to the underlying distribution. So I expect most of the code words in the code book to be, therefore, in the strongly typical set. So how many do I expect not to be in the strongly typical set? Well, hopefully not more than an exponentially small fraction. Right? So that's this event over here. Now, this statement being made is actually stronger than that. This is saying that the probability over random codes that your randomly chosen code, so this C is actually a randomly chosen code, that your randomly chosen code has this property, has too many atypical code words, is super exponentially small. Okay? Because remember, the total number of code words is itself something like n times 2 to the nr. Right? So only a small fraction, only a super exponentially small fraction, only a double exponentially small fraction of those code words have too many atypical code words. Okay. Now, this statement is actually stronger than we really need for the channel coding theorem, but I just wanted to do a slightly more sophisticated proof than you would normally see, because this sophisticated proof gives you something extra which is useful in some contexts. Okay, some contexts that we'll see later, like list decoding or things like that. So this statement is basically saying that the vast majority of all codes have mostly typical code. So how do you see this? So look, the probability that a single x drawn according to this input distribution is not in the typical set is exponentially small, right? This is the usual atypicality analysis, the Stirling's approximation, Pittsburgh's inequality, concentration inequalities, right? So therefore, the expected number of code words. So this is the probability for a single code word that it's atypical. So how about the expected number of atypical code words? Well, that's just going to be this probability times the size of the code word, right? Because the probability of a single code word being atypical was this quantity that we're calling capital delta. So the expected fraction, expected number of atypical code words is going to be the size of the code times this fraction, which is delta times c, right? So remember, what do concentration inequalities allow us to do? So we have this quantity over here is delta times C. So we have some random variable, and hopefully it concentrates. So the expected number is something like this. So what is the probability that the actual number is much larger than the expected number? We want to bound that probability, right? So the probability that the actual number of code words um, is larger than this quantity over here. So we'll give ourselves some slack. Notice this 2 over here, right? So this 2 over here, it's like taking a square root of this delta, right? So, and since delta itself is a small quantity, therefore this is like saying the probability of there being many more than the expected number of code words. That's a probability we want to concentrate, right? So this quantity over here is just, you just write down the tail bound over here. Okay, you know what, I was ambitious. So we're not going to be able to do more than this. So that's all we'll do today. So let's just focus on this. Okay, this proof technique is going to be useful later when either in a homework or something else, I'll give you some list coding. Okay, so what is this probability going to be? I mean, you could do it directly by the Chernoff bound, but sometimes it helps to do these calculations just by brute force. So let's see how you get this. So this is less than or equal to so the number of code words could be could be the square root of delta times the size of C, or that plus 1 or that plus 2. So you have to sum up over all i's larger than this quantity over here, right? So it starts from j going from square root of delta times C till the size of C, times the size of C, choose j, delta to the j, 1 minus delta to the C minus j. Right? This is just the tail bound. Okay? Because what's happening over here is, okay, people are looking a little bit mystified. So remember, what are we trying to compute? We're trying to compute the probability that the number of atypical code words is too large. Okay? So we have some set here. This is script x to the n. We have some typical set over here. This is This is the typical set of x's with some slack delta n over here. Right? Now the probability of so now we have two events. Either you're in the typical set or you're outside the typical set. Okay? So it's just a binary random variable. And this binary random variable is outside the typical set with pretty small probability. It's outside the typical set with probability delta. Right? Delta, remember, is just, well, it's an upper bound on the probability you're outside the typical set. Right? So now you're trying to compute how many code words are going to fall outside the typical set. That's what you're computing. So therefore, this is the right summation to look at, right? You sum up over j being larger than the number you want to, your threshold up till all of this, and then you just sum over all possible values of j going from here to here. So C, choose j, delta to the j, 1 minus delta to the C minus j, right? That's it. And now the tricks that are useful are, often in these contexts, you can just bound this last term. So this is a 1 minus delta. Delta is positive. So you can just bound this from above by 1. Okay? And then you don't have to worry about this last term. Makes it easy. Okay? Then in the remaining terms, so here now you have something that's exponentially large, something that's exponentially small, and a summation over here. Okay? So the next trick is, the first term in the summation is largest. Why is this? So okay, so this I'll leave it to you guys to try as a homework exercise. For now, it's an optional homework exercise. Later on, it will actually probably become part of a homework. So you may as well try it now rather than later. Okay. So suppose someone gives you a random variable where you have, it looks kind of like a binomial or a Gaussian or whatever, and the expected value is somewhere here, and now you're trying to bound the upper tail. Okay. So you clearly expect the first term to be the largest, right? That's what we're trying to do. So one way of proving that the first term is the largest is just to take the ratio of the first term to the next term, or in general, the ith term to the I plus 1th term. Okay? Take the ratio of those things. So if you look at this over here, you have a C choose J delta to the J, and you'll have a C choose J plus 1 delta to the J plus 1. Okay, so this becomes a little bit larger, but on the other hand, this becomes smaller. And the way that this works is when you take the ratio of these quantities, the ratio is going to be less than 1. Okay, if you take the jth term versus the J plus 1 term. So just try it as a hopefully not too challenging homework exercise. Okay? All right. So the first term is going to be the largest. So therefore, you may as well just take all the terms over here together and view them as so you may as well just bound this from above by the first term and just use a loose bound, just multiply by the size of C. Then use Stirling's approximation here, so or even a weaker form than Stirling's approximation. So really, like when I replace this C choose C choose J with this exponential quantity here, I'm really just using a weak form of Stirling's approximation, and then it's algebra, and you get a double exponential. Okay. I went a little bit fast, but really it's just algebra, and I've given you the hints as to how to do it. Hopefully recorded, so you'll be able to do it. So again, this proof technique, this brute force proof technique, sometimes the concentration inequalities that you've studied, Chernow-Pond and so on, in certain regimes, you cannot use them directly. And it helps to be able to do these calculations brute force by hand. So that's why this is useful to do. Okay. All right, that's it for today. And we're sort of halfway through the general channel coding theorem. You've already seen the binary symmetric channel, so you're in good shape. Next, we'll pick this up and we'll look at a whole bunch of other things. We'll look at the Blahout-Arumoto algorithm, which gives us a computationally efficient way to compute the channel capacity, because otherwise, you may have to do some very messy algebra and it's not clear how to do it and so on. And then look at certain properties of the channel capacity function for so-called weakly symmetric functions. We'll show that thing that I claimed earlier, which is if you have noiseless feedback, then it doesn't improve the channel capacity. We'll look at, but it may lead to easier encoding schemes. So we look at the Weldon scheme, which is a scheme which allows you to encode and decode much more easily than the channel coding theorem, computationally efficiently. And then what is this here? Oh, right. So yeah, I had pointed to the fact that that once you have non-point-to-point channels, then things get more complicated. So for example, here you have a multiple access channel. So you have two transmitters and one receiver. And in this case, some strange things can happen. So for example, you may want to do some joint source channel coding, whereas in the point-to-point setting, you can show that you can separately do source coding and channel coding separately. Okay, I'm giving you a whole bunch of sneak previews, but we'll dive into all of these things later. So more detailed things to do with the channel coding theorem next week. Okay. Thank you for your attention. And during the break, I was not able to follow the discussion about the midterm. So let's if you have time, let's very quickly get a sense of the class as to when you think midterms might work. We can follow it up on the answer. Okay. So any thoughts?